Welcome to the Academy for Teachers Masterclass on Rocks, Water, and Life on Other Planets with Lindy Elkins-Tanton. I'm Bianca Brandon, and I've been teaching science for the past 18 years at Staten Island Technical High School. I love what I do for so many reasons that it's hard to know where to start. I remember sitting in my own biology class in high school and dissecting a frog and an earthworm and a crayfish, and I was just hooked on biology after that. And part of the reason I became a teacher is because I wanted to share that excitement and enthusiasm for my subject with my own students. In fact, one of my former students who took both my AP biology and forensic classes is now in a pathology residency program at UCLA. And he recently emailed me and said that he had performed his first autopsy and that it made him think of me. And as odd as that sounds, it really filled me with pride. I am also proud to be a fellow of the Academy for Teachers, an organization that has stoked my passions, made me smarter, and has inspired me to bring a whole new level of scholarship to my classroom. During my master classes, I've had the pleasure of meeting preeminent researchers, learning from Jane Goodall, meeting Henry Louis Gates Jr., learning, and of course, learning from my most brilliant and esteemed colleagues, my fellow teachers. I have the honor today of introducing Lindy Elkins-Tanton. Lindy is Principal Investigator of the NASA Psyche mission, Managing Director of the Interplanetary Initiative at Arizona State University, co-founder of Beagle Learning, and she is a professor at Arizona State University as well. I'm personally so excited to be taking this class with Dr. Elkins-Tanton because the topic links biology, my life's passion, with space travel, something that just fascinated me as a child. I grew up in the 1980s watching the space shuttle flights on television and dreamed of a day when humans might colonize other planets or find life on other planets. But Lindy is not the only star of this masterclass. It is also my honor to introduce the 21 teachers here today who were selected from many applicants. This is an impressive group with advanced degrees in education, molecular biology, geochemistry and biostatistics, conservation, and earth science. We teach grades 6 through 12 in public schools, charter schools, and independent schools. We teach some really interesting subjects like geoscience, sustainability, forensic science, mechanics and relativity, robotics, and astrobotany. The number of extracurricular activities that we supervise is mind-blowing. We are advisors for the Green Team, the Gay Straight Alliance, the Cooking Club, the Comedy Ensemble, and many more. We coach Science Olympiad, track and field, and the swim team. There is a lot of teaching experience here today. We've been in the classroom between 4 and 37 years. The total number of years that we've been teaching is 331. We teach between 32 and 170 kids. The number of children who know our names is 2,171, and that's this year alone. So your real audience today, Lindy, are those 2,171 kids, because every teacher here will in some way share with them what we learned from you. The ripple effect of a masterclass is huge. Thank you, Dr. Elkins-Tanton, for being here. Thanks to my fellow teachers for teaching. And with that, let the masterclass begin. Take it away, Lindy.
Awesome. It's so good to meet you all. I'm really excited. How's my sound? Is it good? Okay, good. I have to tell you, we're having a crazy moment right here in Arizona. Wait for it. It's snowing in Phoenix. It does not usually snow in Phoenix. It's pretty exciting. This started just as our class started, so it's some kind of sign of the importance of what we're doing. All right, let me start up my screen. Now, Renee, you and I talked about a way to do questions. Can you remind me what our clever, brilliant idea was?
Our clever, brilliant idea was that when students had questions that followed on what you were saying or clarification questions, that they should raise their hands. But if they wanted to start a new thread, they would put it in the chat and we would come back to it.
That seems really perfect. So I am not going to be watching the chat, but I absolutely invite you to just unmute yourself and shout out at any time any questions that you have. I'm really, really comfortable with that. And so, and lest I forget, what I'm going to talk about today is more or less a few parts of a series of 9 lectures that I gave over the last year and put up on my YouTube channel. And so if you all want kind of the slightly more detailed version, it's there for you. It's obviously free and open to the public. And so let's talk about rocks, water, and life on other planets. This beautiful illustration is from Sam Hollish, as you can see at the bottom. He's a Psyche-inspired creative. And this is a program we have for undergraduates at any 2- or 4-year college in the United States. They can compete for, they can apply for, and become an artist to work with the Psyche mission. And every year we take 16 such creative people and we actually fund them to create 4 original works of art each over the course of the year. And this is one that he made that I particularly like. And so we are talking in our breakout group about disciplinary silos versus connection among disciplines. And I would attest that every discipline is connected to every other discipline. And I would just like to start that way because I think it's very fitting for this conversation. So let's see, here we go. All right, so let's start by putting everything in perspective. So here is a timeline that starts on the right with us right now, and then moves to the left through the age of our universe, which began at 13.787 plus or minus 0.020 billion years ago, GA billion years, giga annum, the age of the universe. Big Bang Theory says that 100 seconds after the origin of the universe, the temperature was 10 to the 9th Kelvin. And 30 minutes later, the universe was 72% hydrogen, 28% helium, and trace amounts of lithium and beryllium. But by 4.567 billion years ago, which is the beginning of our solar system, stars had been formed and grown and died over as many as 6 generations. And those stars had made all of the elements we have in our solar system. Our sun is probably a 3rd generation star. And that's lucky because hydrogen, helium, lithium, and beryllium is not enough to build the beauty around us. We need all those other elements. And that leads right into how are we able to have life on our planet's life as we know it. And so here's the timeline that we're going to use for this conversation today. From now back to 4.567 billion years ago, the first solids that appeared in our solar system. So I'm going to start with rocks, and I'm going to work forward to having rocks that are habitable. That's what the goal is of about 30 slides that we have right now. And so here's that same timeline, just 5 billion years worth of time. One of the problems we have understanding planetary science and astronomy, of course, is the gigantic distances and the immense depths of time. And I'm sure that you struggle with this with your students when you talk about this kind of thing. And so see that little vertical orange line under the timeline? I'm going to put an arrow to it to make it a little more obvious. That's the span of time I'm going to talk about first today. Just the few million years before and up to the first solids forming. This is the rocks part of rocks, water, and life on other planets. And so that's where we're starting. All right, generations of stars are seen in this infrared image from NASA's Spitzer Space Telescope. In this star-forming region, it's called W5, by the way. The oldest stars, you can see them as blue dots in the centers of hollow cavities, and the clouds of gas and dust are in red and green and white. Younger stars, you can see, line the rims of the cavities if you can look very closely, and some can be seen as the pink dots at the tips of pillars like this one right here, if you can see that one. These are pillars of gas and dust, and the white areas are where the very youngest stars are forming. So W5 spans an area of sky equivalent to about 4 full moons, and it's 6,500 light years away. This, however, is very dark invisible light. All the color we're looking at here are in infrared wavelengths. And so why am I showing you this? Because this birthplace of stars is also the birthplace of planets. And by looking out into the universe using telescopes is one of the ways we figured out how stars and planets are born. Those stars are born from the gravitational collapse of dense fragments of these giant molecular clouds, which is what this is called. And the collapse is probably triggered by a shock, like a nearby supernova explosion. So a star explodes, and its shock wave comes out and it tears up parts of this molecular cloud and crushes them together, and they begin to condense and then fall together under their own gravity. And that's how a star is formed. And so the first thing here is that solar systems form from giant molecular clouds. And these clouds are mostly hydrogen, a little bit of helium, and a tiny bit of dust. And that dust is, frankly, everything to us. I mean, we do have plenty of hydrogen in us in the form of water, but everything else comes from that dust. So we are just the trace of the trace, which I think is so interesting. And the density of these giant molecular clouds are between 100 and 10 to the 6 molecules per cubic centimeter, which seems like a lot until you realize by comparison, air at sea level has 10 to the 19th molecules per cubic centimeter. And so it's pretty sparse, a giant molecular cloud, but that's where stars are born. And so that's where we start from. All right, now what happens to that collapsing giant molecular cloud region? The collapsing molecular cloud falls inward and it becomes a protoplanetary disk. This is a protoplanetary disk, or rather it's an artist's drawing of a protoplanetary disk. The center of this spinning disk of gas and dust becomes the protostar, a star that it's not yet undergoing nuclear processes, and the disk is the birthplace of the planets around the star. So though we cannot look back in time and see the dust that formed our solar system, we can use telescopes to look out at young stars elsewhere in the solar system, elsewhere in the universe, in our galaxy, really specifically. We can look elsewhere in our galaxy and see the disks around young stars, and we can see different ages and how they evolve. And so this is an amazing thing, actually, that we've come to know in just the last decade or so because of the intensity of study of exoplanets, planets around other stars, that almost every single star is born with planets. And so keep that in your mind, encourage your students to keep it in their minds when they look up into the night sky. Almost every single star you see has planets orbiting it. I mean, to me, that is really mind-blowing. It changes the way I look at the universe. So let me just have a brief conversation then about why solar systems are shaped like disks. This is a very common question that I get from students. So here's the region of the giant molecular cloud that's collapsing under its own gravity on the left. It's basically a sphere, a region. It's spinning because there's some net angular momentum in the cloud on, if you add up the directions and the momentum of all of the molecules and gas, there's some common direction of spin. And so, so there's some net angular momentum. Now, all the gas and the dust in that spinning ball feels both the pull of gravity toward the center of the ball, and it feels the centrifugal force that would cause it to move further away from the center of the ball. The material at the edges of the equator, where I've drawn these arrows, is moving the fastest and feels the most centrifugal force. And so the disk develops in a plane perpendicular to the axis of rotation, which is this, where the centrifugal force can balance the infall. So this material is feeling gravity pulling it down, and this material is also spreading out. And so that is why these balls of gas become disks. And now we're getting really close to making planets. Now we've got a protostar that's falling together under its own gravity in the middle, and we've got this spinning disk of gas and dust. Now I'm going to show you a complicated slide just to make a few specific points. This is what theory says these protoplanetary disks are really like. It's kind of amazing to imagine. So this is just a cross section of the disk with the baby star on the left, and then there's a gap here, and then there is the disk that goes out and flares out. Now, I want to bring your attention to a few specific things. Close to the star, maybe 1/10 of an astronomical unit, and recall, I'm sure you know that an astronomical unit is the distance between the sun and the earth. So just 10% away from the sun compared to the earth. The temperature is very high, 1500 C at different points in the disk evolution. But when you go further out, like where the earth formed, it's only about 700 C, and when you go further out, it gets really cold. So right away, you might be thinking, well, maybe ices could actually accumulate and stay out here where it's cold in the disk, but close to the center, those things would have to be plasmas, like they would actually be broken apart into their individual elements perhaps, and maybe they would be picked up by these magnetic fields because the disk is charged and spinning and therefore making a magnetic field. The sun is charged and spinning and making a magnetic field, and the magnetic field lines actually interfere with each other. And so material can be flung outward from the inner part of the disk. It's heated very hot. Right away, you might be imagining, and you would be exactly right, that you can make different kinds of planets under these different circumstances in the disk. Now, there's a lot more to it than just that, but if you just think about the idea that they're being strafed by crazy hot temperatures and magnetic fields very close in, but out here, it's relatively calm and cold where ices can form, that's kind of a good set of things to remember from the complexity of that disk. Now, here's a piece of meteorite from the Allende meteorite. It's named Allende because it fell in a region with a town called Allende. Every meteorite is named after where it fell on Earth, and so you get some really crazy, fabulous meteorite names that are unpronounceable to a native English speaker. This meteorite, Allende, contains the oldest known material from the beginning of our solar system. Like in this red circle is one. They're called calcium aluminum inclusions. They're made mostly of calcium and aluminum. These are the first elements that are willing to grow, I'm just like lost my noun if that ever happens to any of you, condense from a plasma in the very hot disk, the very first elements to condense, and they actually give us that age. And I always ask my students when I'm teaching undergrads to repeat it with me, 4.567 billion years ago, the age of the first solids in our solar system. I used to joke my undergrads that if they could not memorize that number, that was the one thing that would cause them to fail the class. They had to remember 4.567 billion, the age of the first solids in our solar system. And there it is from the Allende meteorite. That's what they looked like, little pebbles, little funny little pebbles. And then I want to also show you something really cool if you don't know about it. And I'm curious, oh yes, there it is, the calcium aluminum inclusion used to date the first solids in the solar system. I wonder if you know about pre-solar grains and interstellar grains. I'm actually really curious to know how many of you have ever heard about this before? Are there some who've never heard about this before? So some people have heard of it, maybe some people have not. So more than just gas and molecules of dust formed in our solar system, pre-solar grains are found in meteorites. They're mostly little tiny pieces of diamond and carbide, and also interstellar grains that formed before our sun and from between and out in the solar system, out in the galaxy beyond our solar system. Some of them even fall to Earth today. So these are mineral grains from outside of our solar system. They predate the calcium aluminum inclusions. They predate the things that make our planets. Identified phases in pre-solar grains include diamond, really tiny ones, like 100 atoms in a piece of diamond. Silicon carbide, graphite, corundum, spinel, all kinds of things. Some of them are as big as a micron, but they're very, very small. But several lines of evidence, including the isotopic makeup of their atoms, the deuterium to hydrogen ratio, things like that, demonstrate that they came before disk forming processes. And I read recently about somebody who was collecting interstellar grains out of the mud in his rain gutters. And I think you would be able to find it if you Googled it. And I think that would be the most amazing science activity ever, to collect interstellar grains from the mud in your gutters. And so far, this is where we've come. Parts of giant molecular clouds collapse because of a nearby shock, and these parts spin and they flatten out into protoplanetary disks, in which small pebbles called calcium aluminum inclusions begin to form as the dust in the gas cools, and those first little calcium aluminum inclusions date to about 4.567 billion years ago. Now, something that we teach generally using a completely open inquiry process. And one of the things that we use in the classroom is something that we call the natural next question. So this is not a question about the content you just learned, but it's almost a research question. It's the question you want to ask about where we go next. What's your natural question about where the next thing you want to learn? And so I actually want to challenge you to give me some natural next questions, to unmute yourself and actually share with me what your things that you immediately want to learn next in this story are, because that will help me as an instructor. In our class, what we do is we list them all and then we vote on them, and whichever one wins is literally what we study next. And so if I'm really lucky, some of you will naturally ask questions that will take us to the next part of my talk, and then I'll feel I've succeeded. So I'd love to hear if anyone has a natural next question jumping to your mind, where are we going next? I'd love to hear it.
From this typical beginning of a planetary system, how does the variety of different specific planetary systems arise?
Yes.
And what are the what is the range of possibility?
Oh, yeah. That is great. I'm definitely going to hit on some of that, and you can just point out that if I don't talk about the range of possibility, remind me, okay? Because that's a really great question. Anybody else?
I'm curious to know more about the different kinds of planets that form at the different parts of the disk.
Excellent.
I'm going to talk about that next. And there's a
Related to
lot
that.
we don't know. Sorry, go ahead.
No, related to that, I mean, I don't know if we can use our solar system as a model, but that very distinct demarcation between the rocks and the gas giants.
Yes, the snow line, they call it.
Yeah.
Yep. Yeah, you know, that is a really big mystery. I'm just going to say something about that right now. There seems to be a line right past Mars where after that, suddenly there's gas giants. And that's a pretty stark line. And it might not be entirely from the primordial disk. It might be from later movements of the planets as well. And just because I wasn't going to talk about that later, even though it's such a great question.
Yeah,
Is there one more?
If Jupiter's part of that mess.
Yes, it is Jupiter. It's the main problem that we have in our solar system. It's the big elephant in the room.
I've got one. I've got a question about pre-solar grains. Are some asteroid families more likely to contain pre-solar grains than others?
Yes. Yes. I'm going to just answer that quickly because I wasn't going to come back to it, but so I'll talk a little bit about planetesimals or proto-asteroids that differentiate. They form a metal core and a rocky exterior, and others that never melted. And so we generally don't find them in the differentiated kind, but only in the primitive kind that never melted, partly because they just kind of get lost, I think, in the differentiated bodies. And I talked to the guy who discovered the first ones at University of Chicago one time. He was dissolving meteorites, chondritic primitive meteorites, in order to put them through a mass spectrometer. And he kept getting this like gritty sludge at the bottom of his beaker that he couldn't get rid of. And finally he realized it wasn't an error. It actually was stuff that he could not dissolve in acid when he was dissolving the meteorite. And he looked at it really closely, and it turned out it was a giant pile of tiny diamonds. And so it turns out, and I can't tell you which, isn't that amazing? I can't tell you which is which, but some of the really primitive meteorites have way more than others, and I just don't know the answer. Is there one more?
You mentioned the question of differentiation is sort of an important concept, right, at this point, and its effect on the origin of life, I think.
Oh yeah. Yeah, that is, oh gosh. And so please make sure that I come back and talk about that at the end, because amazingly, there's not a straightforward answer to that question. And yet it's a really, really important one. So I love that. Okay. Thank you so much for playing the Natural Next Question game. We are going to do that one more time. It's incredibly helpful to me. So I appreciate that. All right, so here we go. Now, part two. Starting from just dust and gas, how are the range of rocky, gas-rich, and icy planets built? So I was kind of lined right up with what you're thinking about, which is great. What are the processes that we have good evidence for, and which parts are still poorly understood? Spoiler alert, an awful lot of this is still really poorly understood. The planets had all finished forming by 100 million years after 4.567 billion years, and some were much faster. Mars was pretty much completely Mars in just 5 million years, just 5 million years on this giant, giant scale. And of course, our planets are still being built by the infall of meteorites and micrometeorites and regular meteorites and dust, but they're just growing really slowly. And so do you see that tiny, tiny line right there? Now we're going to talk about the 5 million years after the first solids. That line is approximately correctly scaled to be 5 million years. That's how long Mars took to completely grow and be Mars. Isn't that astonishing? So fast, so fast. This is another example of how time scales have made it very hard for us to figure out geology and planetary science in reverse. All right, so this beauty right here is an idea of how planets formed. So in Western science, before the 18th century, people thought that planets came from outside and just wandered in and joined the sun, which is a lovely poetic notion, which is maybe not totally wrong, because now we've had a couple of interstellar objects fly through our solar system, Oumuamua and that other one, I can't remember what its name is, objects that are not gravitationally bound to our sun, just passing through. And so it is possible that we could grab things from out of interstellar space, but that is not really how planets form. So this beautiful figure is from Svante Arrhenius's 1908 book about Emanuel Swedenborg. And so Swedenborg, this is his original plate from his book in 1734. And so that book in 1734 by Swedenborg, he hypothesized that the planets came forth from the sun by means of centrifugal expulsion. So that's not too far off, right? It's a much closer idea. I will tell you, I have no idea what he is trying to show us in this figure, which is obviously really detailed and purposeful and labeled with numbers. I have no idea. I think the middle thing is the sun, but that's so beautiful and evocative. I just love to show it. After him, Kant weighed in on this and also thought that the planets came from the sun, and Laplace based much of his work, amazingly, on geology. In fact, Laplace, shoot, what is his name? Okay, quick, quiz question. Who are the two famous people who created calculus?
Leibniz and Newton.
Leibniz, I couldn't think of Leibniz. This is, again, my beautiful problem with names and nouns. 10 points, thank you. So Leibniz, you might know, was not primarily the inventor of calculus in the early part of his life. He was a mining engineer, and he worked in the silver mines in Germany, and his job was to keep them free of water. And he noticed that when you go down in the mine, it got hot. And he did a super simple thought experiment. The Earth is a sphere. It's hot on the inside and cold on the outside. Therefore, we have a temporal process going on, which is heat loss from the inside to the outside. Therefore, if you look back in time, it was hotter. And he invented the idea of a magma ocean. He didn't call it that, but the idea that the Earth was once molten. This is true. And this is what I've spent most of my career working on, and I'm really not going to talk about it at all today. But Laplace read that, he thought it was fascinating, and he started working on heat transfer. And so, as I tell my beloved mathematician husband, earth science is the foundation of mathematics. So there you have it. Yes. George Darwin, Darwin's son, suggested the planets were removed from the sun by angular momentum through tides. He wrote these big books on tides. And then finally in 1969, a man named Safronov at the Schmidt Institute of Physics of the Earth in Moscow really laid the foundation for how modern planets, how the modern theory of how planets are formed. And he wrote this amazing book in 1969, full of the equations of how material can clump together and accrete and stick together and form planets out of disks. And so he is really kind of the father of modern planetary science. It's pretty new as sciences go. We're still really figuring it out. And as you all know, we get it wrong over and over again, but we get it a little bit more right every time. And so we're certainly in the probably mostly wrong, a tiny bit right part of our science. And so here's where we are. So we've talked about the things on the left are the things we've already talked about. We've talked about the disk of gas and the first solids in the form of calcium aluminum inclusions. And then on the right, and at the very far right, is a planet, which you can see from my schematic is red on the outside. I'm saying that it was melted on the outside at some point, and that it grew from the impacts, accretionary impacts of smaller bodies. And so the red really implies melting in all of these cases. And look at the small bodies, the planetesimals on the far left side. One of them is molten on the inside, and one of them isn't. So the one that isn't is one that never differentiated. And the ones that melted are the ones that were able to form a metal core and a rocky outside. And that is the other thing that I spent most of my career working on, is that process of differentiation in small bodies. Differentiation meaning the formation of a metal core which sank through density, because the metal is twice as dense as the rock that forms the outside part of the planet. But wait, what happens in the middle? First, we've got tiny pebbles, and then we've got planetesimals. And these planetesimals that I'm showing here, it just means little planet, obviously planetesimal. They're tens to hundreds of kilometers in diameter, we think. So we went from a centimeter to tens of kilometers to hundreds of kilometers, and something in between happened. And so there's my asterisk, and I joke that that is the universal scientific symbol for then a miracle occurs. Because really there are two mysteries in that asterisk. One is, how do planetesimals form? And the other one is, how do planets build so quickly? How do you move from something that's just tens of kilometers in radius up to Mars in 5 million years? And it turns out you got to get to Jupiter in about the same amount of time. And I'll explain why that is. So they're kind of two miracles. And really until like almost 5 years ago, these really had no answer at all. And now at least they have plausible answers, if not correct answers. And so let me talk about those, because it's kind of cool to, maybe some of you guys know about this stuff, but it's very cool to learn about the really new stuff. All right, so mystery number one, how do gas and dust accrete into rocky, icy, and gas giant bodies? Well, pebbles are too big for Coulomb forces to stick them together. So what is a Coulomb force? I think everybody knows this. It's the attraction of oppositely charged objects. In this case, I'm drawing little dust bunnies like you'd have under your bed. And actually they can stick together, like we'd call it static electricity. They can stick together through Coulomb forces. But instead, if you had a couple of pebbles, actually nothing happens when you have pebbles. And so, I mean, it's just a silly graphic, but the strength and the range of Coulomb forces cannot hold pebbles together. And so that's a no-go. So then we would think about gravity. Keep in mind that these pebbles and this dust are orbiting the protosun. They're moving through space at some relative velocity, and we'd like to have them begin to stick together to make bigger objects. And so just like the two rocks you hold in your hand don't stick together through mutual gravity, the pebbles and the small rocks that are orbiting don't either. They're too small for gravity. And so then it turns out that you can't even kind of make them stick together in space if you allow them to impact each other, because most collisions in orbital circumstances, and this is theory, but also there's some experiments, most collisions between bodies between 10 centimeters and a meter are destructive. And bodies between 1 and 10 meters, all collisions are destructive. So no collisions cause them to stick together. And so this was a huge problem. We knew perfectly well they stuck together because here we are standing on a planet, and we really had no idea how. And by we, I mean other people, because I've never worked on this. And so then what do we do? And so we did not know how to take gas and dust to make it into planets. But let's just stop for a second and consider this critical thing. Planets need to form before the gas and dust disk dissipates. Because you notice we do not live in a gas and dust disk around our sun right now. We have planets that are spaced, and they do not have giant amounts of gas and dust between them. So let's think about how much time we have. So it turns out planets have to form before the gas and dust disk dissipates, because that gas and dust is needed to form the gas and ice giants. They need to collect that before it all goes away. And it goes away by being pushed out of the solar system by radiation pressure and by falling into the sun through gravity, and it gets cleared out. So how do we know how long they have? Well, here is a beautiful set of data from the paper I'm citing at the bottom. And so if you look at this data, what we're looking at is which little stars out in our Milky Way galaxy that we can see with telescopes still have disks. And so the horizontal axis here is the age of the sun, and the frequency of that age have disks. And so they figure out the age of specific stars, and then stars of that age family, and they plot this up. So you can see that over here, almost all the stars that are less than 1 million years old have got disks. And when you get out here at 10 million years, almost none of them have disks anymore. So that right away now you know kind of the limits. It's got to be before 10 million years, unless we're a super outlier. So we want to sort of think about the 50% mark. So on average, what would the answer be? It's someplace in this range. 1.5 to 4 million years on average, the disk goes away. Half the time it's gone. And so generally people say, astronomers say 3 million years. Planets have got on average 3 million years to form before the disk goes away. Remember how thin that red line was on my timeline? Like 3 million years is nothing. It's nothing. And somehow the planets have got to completely form. They've got to go from a pebble, a collection of pebbles, up to Jupiter in 3 million years. And this is a good place in case you're thinking, well, maybe it didn't happen this way for us and we're a special solar system. Well, we're kind of special in the wrong direction. It turns out that on average of all the exoplanet solar systems we've seen so far, most of them do not have as many rocky planets near their sun. They have instead giant super Jupiters, hot Jupiters orbiting right near their sun, sometimes closer than Mercury is to our sun, orbiting right up there. So the average solar system in our galaxy appears to be one with a lot of giant hot Jupiters, and that's not just observation bias. We have enough observations now that we know that we are not an average solar system. We are not an average solar system. We have more small rocky planets than most do. All right, so mystery number one, how do gas and dust accrete into rocky, icy, and gas giant planets? Answer part A is instabilities in the disk make planetesimals. So this is another cross section of the disk. And in the middle is purple. Those are pebbles and big pieces of dust. And the blue is the dust, and the green is gas. So what happens in these disks is that the gas goes on the outside, and the pebbles and the dust fall to the midplane through gravity. And it turns out that this is not something that I would have intuited, but the pebbles and the dust grains, the purple and the orange, are like the middle of a sandwich, actually orbit the star at a different velocity. And so the gas is orbiting at one velocity and the little pebbles are orbiting at a different velocity, and they make like a shear between them. One is going faster than the other. And when you have something like that, sometimes you see it when wind goes over the top of a mountain and it hits the still air on the other side, there's shear, it forms waves. Those are called Kelvin-Helmholtz instabilities. And it turns out those instabilities that are formed by the gas and the dust traveling at different speeds crush big piles of dust together. Does it convince you? Do you immediately go, oh, that makes total sense. It could totally crush the pebbles into bodies large enough that they would self-gravitate. This is the best hypothesis there is. And a whole bunch of different models that people have run seem to work. So this is our best guess right now about how things that are this size get crushed together into things that are tens or hundreds of kilometers across and are self-gravitating. So that's why I have a question mark after this. I do not think this story is done, but last we have a plausible answer. All right, so so now we've made a bunch of small rocky bodies. Now let's make the range of rocky, icy, and gas giant bodies, planets. And so here we go. Answer part B, something called pebble accretion. Now, we're talking about pebbles with the little blue. Pebbles are microns to meter sizes. So those are like the calcium aluminum inclusions. Then planetesimals and protoplanets are things that are tens to hundreds of kilometers in size. So we have little tiny objects orbiting around bigger objects or passing by them in the solar system. And the blue is the gas drag of the gas disk. So it turns out that the gas drag slows down those pebbles to the point that the gravity of the protoplanet can pull them in. And that without the gas, the pebbles are still flipping by so fast that the gravity of these small planets is not enough yet to grab them in. So it only works before the gas disk is gone. It only works to slow down the pebbles to the point that they can be captured into planets before the gas disk goes away. And maybe you're also thinking, well, so you could slow down a few pebbles such that they would be sucked into a planetesimal or into a protoplanet. But it turns out this is so efficient that you can grow the multi-Earth-sized core of Jupiter in less than 100,000 years. And then you've got the rest of your 3 million years to add gas onto it, for it to clump up all the gas and ice that it needs. So my friend Hal Levison was a major planetary formation theorist and one of the originators of this theory. He actually was quoted as saying, it wasn't clear how objects like Jupiter and Saturn could exist at all before this Pebble accretion theory was made. And so the idea is that the gas both helps to crush planetesimals together with these waves, and then it helps to slow down the remaining pebbles to the point that they can be gravitationally attracted and they grow very, very fast. And so that's how these planets grow. So the rocky planets in near the sun grow this way, but then there isn't a lot of gas around and they're not quite big enough to really attract a gas envelope. And you go further out from the sun and the planets can attract that gas and ice, and there's a lot more of it. And then they can grow up into things like Jupiter and Neptune and Uranus. But it all has to happen in 3 million years or less. And that is the amazing story of how planets are grown. Now, before we go on to the completely last part about life, did you catch that thing where I said that the planetesimals were molten inside in that picture of the growth? And so this is like a little quiz. Let's have a little quiz. Why did planetesimals melt? A, because everything was molten in the early solar system. B, because impacts between bodies melted them. Or C, because there was a common radioactive element that now no longer exists. I don't know if any of you happen to know the answer. I did not really know about this until, I guess, probably my PhD when I was studying. Well, so this is actually a question mark. Nobody really talks about it, but it's very possible that there was a lot of liquid rock in the inner disk, like droplets of liquid rock instead of just solid rock that we're accreting. This is actually something that I'm studying right now, so we don't really know the answer to that, but it wouldn't be the popular answer. Other planetary scientists would say, no, that is not the answer. And it's not because impacts between bodies melted them, because that only works for really big things, like things the size of Mars and bigger. When they hit each other, they can melt each other with their energy. The answer is that there was this common radioactive element that now no longer exists. Aluminum-26 with a half-life of only 700,000 years. And there was so much of it that it actually melted the planetesimals. And that is why planetesimals differentiated. Without aluminum-26, we would have no iron meteorites. None of them would have melted and formed an iron core and rocky outside. It's only because of this extinct, short-lived radionuclide. How do we even know it existed? Sorry, what was that?
I was going to say, what makes aluminum-26?
Great question. Oh my God. Guess what makes aluminum-26? Supernovas. Guess what started our solar system collapsing? A supernova shock. So the hypothesis is the shock that started our disk collapsing to make our planetary system injected aluminum-26 into it. And right away that could be crushed into these planetesimals really, really fast, just like I was just describing, tens of thousands of years. Still, aluminum-26 was hot enough and there was enough of it that as long as the planetesimal formed before 1.5 million years, it would have melted. And then as soon as it melts, its metal component sinks to the middle and forms the core and leaves the rock on the outside. And so it was found by Harold Urey in the 1950s because he found these minerals like plagioclase feldspar, if you're familiar with it, where you would expect to find aluminum, he would find a magnesium-26. And he was like, why is there a magnesium in this crystal site for this feldspar that should only have aluminum? And he said, this is a very strange isotope of magnesium. Oh, it turns out to be the daughter isotope of this thing called aluminum-26. And then right away, the whole picture fell into place. I think it's amazing. I love this. All right, so where are we? Here's a gorgeous actual photograph of a protoplanetary disk. It hasn't dissipated yet, so it's less than on average 3 million years old. The gas and the dust are still there shining in the microwave range. And those gaps are probably from planets that are forming. Pebble accretion in action. So here's where we are. Parts of giant molecular clouds collapse because of a nearby shock, and those parts spin and flatten into protoplanetary disks, in which small pebbles, these calcium and aluminum inclusions, begin to form 4.567 billion years ago. And pebbles can't be stuck together with Coulomb forces or by gravity. So probably planetesimals were formed by having great regions of pebbles crushed together by waves in the disk. And then pebble accretion does the rest. The gas slows down the remaining pebbles and they're sucked into those planetesimals. And then they can collect gas and ice as they grow. And then there's this cool thing, plus aluminum-26, the now extinct short-lived radioisotope that heated and melted the planetesimals. So that is the story so far. Yes, please.
Sorry, can I ask one more? In that picture, how many planetesimals do they guess there are? Does anybody make that guess, or does nobody care?
So I guess what they would say is this is probably the inner disk gap, and you might have one, I don't know, is that 2, 3, I'm not sure, 4, 5, 6, 7 planets that are forming. And you can kind of do the math of how many planetesimals are required to form something the size of Earth or the size of the core of Jupiter. And it's many thousands. And so that would be the guess.
Another question?
Yes.
How does the shape, or I guess even the structure of a protoplanetary disk change when you have a binary system?
Oh, wow. I do not know the answer to that. That's got to be something pretty complicated. I would guess just that the inner edge of the disk is much farther out. But I've never seen an example of one myself. Does anybody have just 1 or 2 natural next questions to help us guide into the next and final section?
If most of the gases are pushed to the outer edge, how do inner rocky planets develop atmospheres?
Perfect.
Develop atmospheres.
Yes. All right. That is the only one I need. It's so perfect. Thank you for just knowing where I was going. Actually, is there another one? I'd be happy to type another one if there is one.
Well, I wonder along with that, if we end up with the metallics at the core of the, I mean, I know we're exploring Jupiter to figure out what is at its core, but I'm wondering is that some of the metallic elements end up being the center of those gas giants?
So like how did the center of the gas giants end up being metallic?
If they are, yeah, I mean, it's just what is the gas coalescing around?
Oh, yeah. Right. Okay, sorry, I'm not in gas giants. If the inner part is metallic. So it's thought that they start with a rocky core. So there could be still a rocky core in the very middle of those gas giants, but then around them will be a metallic envelope of metallic hydrogen because the pressures are just so high. But they don't start out that high, right? They start out small pressures, and then as it grows, the pressure in the interior gets higher and higher. So that's that story as I know it, but I'm not a super Jupiter expert. All right, so here's where we're going in the last few slides when we're getting to the life part. So now we're talking about what is a habitable planet, and it's all the rest of our time, right? All the rest of our time. After 4.5, about 50 to 75 million years after the first solids was our moon forming impact. That was the last giant impact of the growth of the Earth, and it melted the Earth probably all the way to the core. So that's our fresh starting place for the Earth as we know it, and that's where we take off from there. So here's this image from the paper, but with some additions. So let's start by looking about at what we've discovered so far about the extreme conditions under which life can live. So first, getting oriented to the figure, the horizontal axis along the bottom and the top gives the pH. And I think you guys are all pH experts. And if you look up at the top, I've given examples of the kinds of pH that are sort of familiar materials to calibrate us to the scale. So on the top left is battery acid, about 1, up through rain, depending on where you are and what decade it is. And then neutrality and up to bleach at 12.5. And then on the vertical axis is temperature in both Fahrenheit and Celsius. And again, on the left, I put some familiar temperature conditions from the coldest temperature measured on Earth, right up the scale to the boiling point at 1 atmosphere. And so that kind of is a way to lay out the conditions we have on Earth. The rose-colored regions on the graph show the range of conditions for certain Earth locations. So conditions in black smokers up here in this rose-colored box, and then hot springs right here, and those black smokers can have liquid water at temperatures even above the boiling point of water at the surface because of its pressure, right? And so, and if you look at that green star, strain 121, these are the living conditions for the microbes that have been found. So there's one that lives at 120 Celsius above the boiling point of water because it's got so much pressure. Isn't that nuts? It's so nuts. And no light, by the way. So my friend Everett Schock, who's a very brilliant astrobiologist, reminds me every semester, do not be distracted by photosynthesis. Almost all primitive life, probably most life in the universe, is not photosynthetic. Do not be distracted by the use of photons for an energy source. And so these guys do not use photons, that's strain 121. And so notice some of the other green stars. Way on the left is a microbe that lives in acid conditions worse than battery acid. People have discovered life everywhere we've looked for it, even under conditions that you would have thought were impossible. And they have great names. These are some microbes that live at very high temperatures. In fact, Geogemma burroughsi is the new proper name for strain 121, that one at the top of the picture here. But I love Pyrococcus furiosus, because what better name could you have for a microbe living at high temperatures? Isn't that the best? And there are other difficult conditions for life also that aren't even graphed on here. So these two, Deinococcus radiodurans and Thermococcus gamma tolerans, you can guess from their names, they're tolerant of high radiation. Deinococcus radiodurans was found living on fuel cells in nuclear reactors. Now this comes into great importance when you're thinking about icy moons, because Europa, I'm on this, the standing review board for the Europa Clipper mission. I've learned a lot about Europa as a result of helping them build their spacecraft. If you stand on the surface of Europa, it's in the high radiation belts for Jupiter, you will die from radiation exposure in 8 minutes. And so the surface of Europa, not really great for life as we know it, except Deinococcus radiodurans, right? Like, well, there are ways. So what is the one thing that all of these creatures have in common? Well, it is liquid water. That is it. And so water is one of the very few things we found so far that all life we've discovered needs. Water, carbon and other elements, you can add other elements to that because you can't just be made of carbon and hydrogen and be alive as far as we know. Water, carbon and some other elements, and then a source of energy. And that's about it. And energy can be many things. And as you know, don't be distracted by photosynthesis. You can remember that. In hot smokers on the ocean floor, microbes can reduce sulfur for energy. They take the water and they oxidize the sulfur that comes out, and it's just like fantastic. So, or they reduce the sulfur. And so there are many different ways to find a gradient of obtainable energy that they can take. But we're going to focus on water here and assume that on any other planets, there will be a source of energy and those other elements. And so this is exactly the other question. Where did most of the Earth's water come from, since we formed pretty close to the sun? Even if we migrated a little bit, this is basically where we came from, right here. And so there's that picture, the rocky planets building up. So we're going to cut to the chase, and I'm going to say right now that we have every reason to believe that Earth's water came from this process and was not delivered by later impacts or by comets. The Earth was born wet, and there's evidence for this assertion. And so here's our evidence. Mystery number 2, where did most of the Earth's water came from? From rocky planetesimals, no question mark, for sure. This is basically settled. So as we know, most elements have isotopes, that is, they come in different weights. And different parts of the solar system, different kinds of bodies are typified by different isotopes. And so on the bottom axis, this is deuterium to hydrogen. So deuterium is heavy hydrogen. It's more prevalent in some comets, like these guys, see them up on the high on this bottom scale, compared to, say, the Sun and Jupiter, which basically have the same composition. And so for a long time, people thought that Earth was formed dry, which kind of made sense from our silly Earth surface perspective on chemistry and physics, and that later cometary impacts were certainly what gave us the water. But for a long time, then no comets matched the D to H ratio of the Earth. And then finally, somebody measured this annoying comet that does match the D to H ratio of Earth. However, there's a second axis here, which is nitrogen isotopes. And notice that none of the comets match Earth's nitrogen isotopes. And that's true for many, many other volatile elements as well. So if comets had delivered Earth's water, they would also have delivered nitrogen. They would have delivered other elements that do not match. Noble gas compositions on Earth limit cometary contributions to 1% or less. So Earth's water exactly matches water from a class of meteorites called enstatite chondrites. does not match comets, not in any way. So here is an enstatite chondrite. This is the philistfer, it's very hard to say, enstatite chondrite. I took this picture at the University of Alberta about a year ago. The shiny parts are metal and the brown parts are rock. So where is the water in this little equation right here? Looks like a nice solid rock with little bits of shiny metal in it. There's no water, there's no ice in it. And in fact, these rocky building blocks do not bring water in the form of ice, but instead as part of their solid minerals. There are minerals that contain water as part of their crystal structure. They're not wet in the sense we think of them as wet, but they use water as part of their building blocks. And then when they're heated, that water is liberated. So chlorite and serpentine are two examples of that. These two here, I am holding this piece of, or somebody else, it wasn't me, holding this piece of chlorite. There's water bound up in that crystal structure that if you melt the chlorite, gets released. And that's how water came to the Earth, for sure. Matches enstatite chondrites. Now, almost finished. I know we're running out of time, but I think I'm going to hit it kind of right. So here's a graph. This is my last, almost my last piece of data, but I think it's really great to mix data and images. And for you guys who are very good at this stuff. This is the water and carbon content of many kinds of meteorites. Meteorites, let's just get this in our heads straight. Meteorites fall from space. Almost all of them come today from the asteroid belt. And so we don't know for certain that we have the full range of building blocks of planets falling onto us from the asteroid belt. Some might have all been eaten up in planet forming, lost into the sun, but we still have a pretty great library of meteorites that are basically like the eggs in the flour that went into building the planets, if you're building a cake. And so here's water from 0 to just 0.7 weight percent, so not even 1% of water. And here's carbon from 0 to 0.4 weight percent, not even a half a weight percent of carbon. And all these different meteorites plotted in between. Here's enstatite chondrites, the ones that we think built the Earth. So just over a half of a weight percent of water. It turns out, follow along here, make the Earth out of planetesimals made of the enstatite chondrite bulk composition. Eventually you end up with impacts large enough to melt the Earth, and the material gets processed through a magma ocean that then solidifies. We have very good reasoning to think this happened. All of the water will be released from the melted rock in the magma ocean. Some of it will be released into a dense steam atmosphere that forms our first atmosphere, and other little bits of it will trapped in the crystallizing minerals as the interior of the Earth solidifies. So there's still water trapped in minerals inside the Earth today. Now, if you allowed that steam, if you allowed that dense steam atmosphere to cool and collapse from a meteorite that had a half a weight percent of water to begin with, it would make a 30-kilometer deep ocean over the whole surface of the Earth. And so that's more water than we have on the Earth. And in fact, as my friend Kevin Zonley says, the problem is not giving the Earth water in the atmosphere. The problem is having too much. Like, how do we get rid of it so we can have as dry an Earth as we have? So that's the water story. It turns out rocky planets are born with water. And that to me is also like a mind-blown moment. Rocky planets everywhere in the universe are likely to have been born wet and therefore habitable. So when you look up at every star in the sky, knowing that every star, planets think that every single of those rocky planets was at some time wet and habitable, most likely. I think that's pretty cool. All right, last couple of thoughts. This is a water phase diagram, temperature at the bottom, and pressure along here, the vertical axis. And these are the phase regions, the vapor phase region, the liquid phase region, the solid phase region for water. Here's where Earth's surface is right here. And here's Venus, not so nice. Here's Mars. Mars dips into the liquid water region right there, dips in. Here's the ocean on Europa under its ice. These are all places that have beautiful liquid water available if life is at all like anything that we know now. So that's a nice thing to look at with students also, is the phase diagram. So last thought, does the liquid water have to be on the surface? Isn't liquid water perhaps even more likely to be at depth in a solid planet? So here are some photos of ice layers in cliffs faces on Mars. Now we know there was flowing water on Mars in the past. We can see the river deltas now fossilized and dry. We're still searching for liquid groundwater on Mars today. There has not been a definitive identification of liquid groundwater on Mars today. Looks like there might be liquid water under the Mars polar caps, but that recent result is under question. But it does look like there are ice layers here, which means a little bit lower in the crust, a little warmer place, and you end up with some brine. And so I would argue that the most likely thing on Mars is that there are brine pockets in the crust, and it would be really cool to look at them and see if there was life. So here's the other question. What's the most likely form of life we would find? Judging from the history of Earth, I would say the logic of simplicity says the very most likely kind of life is going to be single cellular or multi microorganisms. And I would also argue that the most likely safe wet place on any rocky planet is under the surface. And so I would argue that the most likely form of life in the universe is microorganisms under the surface of a rocky planet. Not easy to find, but probably very likely. And so there we are, rock, water, and life on other planets, some more art from the Psyche mission, and kind of the take home that probably every rocky planet was born habitable with water of its own, and that probably every wet rocky planet had everything else that was needed for life, an energy source and the atoms to make up the life. And so the big question becomes, why doesn't there seem to be life everywhere? Why haven't we found it off the Earth yet? Why does there only seem to have been one time that life arose on the Earth? If Earth is the perfect place for life, why don't we have many advents, many common ancestors, and we only have one? So many mysteries yet to go. That's it. That's my whole talk. I went a little longer than I meant to. If you have any time, I'm really happy to stay and answer questions. I apologize for being a bit longer than I meant.
That was riveting. Thank you so much. I wonder if we could take a few questions. If there are those of you who need to go, please feel free. But if anybody would like to raise their little Zoom hand, why don't we take a few questions? Or alternatively, just jump on in.
Yeah.
Go ahead, Henry.
Thank you so much. That was amazing. I'm wondering if you can say anything about the interplanetary seeding mechanism, and if we do find microbial life somewhere else in the solar system, how we will go about distinguishing its possible independent origin from a common ancestor with Earth life.
This is such a great question. So there's the idea that like Mars beat us to habitability. Mars was habitable before the Earth was. And it was actually my friend Ben Weiss, my colleague, and his advisor, Joel Kirschvink at Caltech at the time, who wrote the seminal paper that demonstrated that impacts into Mars could loft rocks that would travel through space and land on the Earth with, if there was life inside them, preserved, and that the life would not die on the way. It would happen fast enough and the temperatures were okay, and you could actually get life delivered to the Earth from Mars should such a thing happen. Less likely to deliver from the inner planets out to Earth, but still possible, amazingly. And so the question of how we will tell them apart is a gigantic problem. Did it start here and go there? Did it start there and go here? Does it look like Earth life because it's contamination? Can you imagine, this is what happens in my mind at least, decades of fierce argumentation among scientists and continuing devaluation and disbelief of science by the general public because we can't make up our minds. That's kind of what I'm worried about. But I'll add one interesting thing to this. There's a guy whose name I can't think of right now. He's at Harvard. And he believes that life did not arise on this Earth. And the reason he believes it is theory right now, and I'm not a biologist, you guys will know this better, but I'll say the words and maybe they'll make sense to you, that before our DNA life, there was RNA world, supposedly the earlier kind of chemistry when things were getting organized to make DNA, RNA world. He said there is zero evidence for RNA world on the Earth in any fossil record. And he believes it happened somewhere else.
Wow, thank you.
Yeah.
Ben DiNardo, do you want to jump in?
Yeah, thank you that was an amazing presentation. My question is about the recent discovery of phosphine in Venus.
Yeah.
If you could just talk, anything about that. I think that's one of the things I teach an astronomy class, a lot of my kids are interested in, and just where do we go from here? What thoughts on that? Anything?
Oh my gosh, phosphine. Right. So, so there are several sides to this story. So one side is a group claims to have detected phosphine in the Venusian atmosphere. They claim to have detected it at concentrations higher than should be experienced just through inorganic processes. Then that data, they have to release it. People start reanalyzing it. Other groups say, actually, that's well within the errors. We don't think you actually detected anything. So the detection itself is under question. Then there's the problem that phosphine is made through inorganic processes, even on the Earth, organic and inorganic. And so unfortunately, so the punchline to me is, unfortunately, there is no single biosignature that definitively shows life that we can detect in any other atmosphere. People have not even figured out one that is only made by life. And so this one is very evocative, and there are definitely atmospheric sampling missions being planned for Venus right now. And I think it's great because creatures could live in the clouds in Venus, but there's no proof from the phosphine result.
As a follow-up, not even like if we found molecular oxygen in large amounts, that wouldn't be considered a biosign?
So you know what's really frustrating is molecular oxygen gets pulled out of atmospheres very, very quickly through reaction with things like rocks. But if you were on a water world, a world that has no rocks exposed above the water, that has an active atmosphere, a lot of molecular oxygen can be created because it has no sink, it has only a source. And so it is possible to make up a planet that would have an oxygen atmosphere of some percentage that was not from life.
Wow.
I know. So frustrating. So frustrating. I would love to have all of you, and with your classrooms, look at the stuff we have for students on Psyche mission, and so happy to have people come and talk to your classrooms. If you want people to talk about space missions, we've got a super diverse team, really big diversity, gender, racial, ethnic diversity, and huge love for outreach. So really happy to connect with the space mission if you're interested.